In this video, we are going to derive Gauss's law from Coulomb's law. Now we know that Gauss's law says that flux through any closed surface is numerically equal to charge enclosed by the surface over epsilon naught. And Coulomb's law is the law of electrostatic force between two charges. So if I have two charges Q1 and Q2, electrostatic force between them will be given as F equals K Q1 Q2 over R squared, where R is the distance between these two charges. So I have to use Coulomb's law to arrive at Gauss's law. So to begin with, let us consider a point charge Q, and this point charge Q will create electric field around itself. Now from Coulomb's law, if there was another charge, let's say Q prime, present at a distance r from Q, this Q prime will experience a force because of charge Q, and we can write that force to be numerically equal to F equals K Q prime over R squared, where Q is the magnitude of our original charge, Q prime is the test charge we took into consideration, and R is the distance between them. From the definition of electric field, we can find electric field E as force per unit charge. So when I substitute for force over here, we get Q prime over R squared into Q prime. And when you cancel off the Q prime, you get electric field as KQ over R squared, where K can be written as 1 over 4 pi epsilon naught Q over R squared. So this is the value of electric field E at any point because of the charge Q. Now let's say I want to find flux at point P because of this charge. And in order to find flux through point P, we will create a spherical Gaussian surface that passes through point P over here. And then we know from the definition of flux, phi will be equal to integral E bar dot dA bar, where E is the electric field at point P and A is the surface area of the Gaussian surface. Here the Gaussian surface is a sphere since electric field has radial symmetry. So we can write integral E dot dA as E times surface area of the sphere, which is 4 pi r squared. And you can notice from the figure that both electric field and area vector at any point will be parallel to each other because electric field is radially outward and area vector at any given point is perpendicular to the surface pointing outward. So they both will be in the same direction at any point on the Gaussian surface. So you can write your phi as E times 4 pi r squared. So phi will be equal to, we can substitute for E from equation 1. E is 1 over 4 pi epsilon naught into Q over R squared times 4 pi R squared. Now we can cancel off 4 pi and 4 pi, R squared and R squared, and you are left with phi equals Q over epsilon naught, where Q is the charge enclosed by the Gaussian surface. So we can rewrite this as charge enclosed over epsilon naught. This is nothing but Gauss's law. So we used Coulomb's law to arrive at Gauss's law.